Introduction to Bayes' theorem. Hello, everyone. Welcome to today's lecture on Bayes' theorem. We are going to look at Bayes' theorem, which is fundamental to understanding conditional probability and its various applications. So here is an overview. We are going to start with an brief introduction to probability, where we'll cover the basic concepts, and then we're going to look at conditional probability, which is important to understanding Bayes' theorem. Then we're going to introduce Bayes' theorem itself, discussing its formula and significance. After that, we're going to go through some practical examples and applications of Bayes' theorem in different fields. Then we're going to wrap up with a conclusion. So, introduction to probability. In order to understand Bayes' theorem, it is important to have a good grasp of basic probability concepts. Probability is essentially a measure of how likely an event is to occur. So here are some key terms. Experiment. This refers to any process that leads to one of several possible outcomes. To give you an example, rolling a die or flipping a coin can be that. And sample space, often denoted as S, is the set of all possible outcomes of an experiment. So for example, the sample space for rolling a six-sided die is 1, 2, 3, 4, 5, 6. Event. An event is any subset of the sample space. So say we're interested in rolling an even number. The event would be 2, 4, 6. And probability is denoted as P of A, where A is an event and it ranges between 0 and 1. So a probability of 0 means the event cannot occur, while a probability of 1 means it will certainly occur. So now we're going to move on to conditional probability. So conditional probability is the probability of an event occurring given that another event has already occurred. This concept is crucial because it allows us to update our predictions based on new information. So we denote conditional probability as P probability of A given B. So A is the event of interest, and B is the given condition or event that has already occurred. And the formula for conditional probability is probability of A given B equals to probability of A and B divided by probability of B. So this formula tells us how to calculate the probability of A happening given that B has already happened by dividing the probability of both A and B happening together by the probability of B. And this is really important for grasping Bayes' theorem. Now we're moving on to Bayes' theorem. So Bayes' theorem allows us to update the probability of a hypothesis as we get more evidence. And this is widely used in fields like medicine, finance, machine learning, and more. So the formula for Bayes' theorem is probability of A given B equals probability of B given A times probability of A divided by probability of B. This might be a little confusing, so if we were to break this down, probability of A given B, you can think of this as posterior probability, or the probability of event A given event B has occurred, and probability B given A is the likelihood or the probability of event B occurring given that A is true. And probability of A is the prior probability or the initial probability of event A. And probability B is the marginal probability or the total probability of event B occurring. So Bayes' theorem helps us revise our initial assumptions, which is a prior probability in light of new evidence, likelihood, to obtain a more accurate understanding, which is a posterior probability. So let's look at how this theorem is derived. Derivation of Bayes' theorem. In order to derive Bayes' theorem, we will start with the basics of conditional probability. So first, we know from conditional probability that probability of A and B is equal to probability of B given A times probability of A. And this represents the probability of both events A and B occurring, which can be calculated by multiplying the probability of B occurring given A by the probability of A. And similarly, we can express it as probability of A and B as probability of A given B times probability of B. So we can equate these two expressions. So on the left side, we have this probability of B given A times probability of A. And on the right side, we have probability of A given B times probability of B. And then we will solve for probability of A given B. So we need to divide both sides by probability of B. So then we get Bayes' theorem. Now, example 1, medical diagnosis. So we're gonna look at a practical example. Say you are testing for a disease. Here are the details. We have prior probability, which is a probability of disease. So this is the initial probability that a person has the disease, which is 1% or 0.01. And then sensitivity, which is probability of testing positive given disease. So this is probability that the test correctly identifies the disease, which is 99% or 0.99. Specificity, probability of testing negative given there's no disease. And this is the probability that the test correctly identifies the absence of the disease, which is 95% or 0.95. And then we want to calculate the posterior probability, meaning the probability that a person has the disease given that they tested positive, which is probability of disease given test positive. So in order to do this, we would need the total probability of testing positive, and this can be calculated by using the law of total probability. So probability of test positive equals to probability test positive given disease times probability of disease plus probability of test positive given no disease times probability of no disease. And we're going to look at this calculation step by step on the next slide. So given the data, we have probability of disease as 0.01, probability of test positive given disease as 0.99, probability of test positive given no disease as 0.05, and then probability of no disease equals to 1 minus probability of disease, which is 0.99. So we calculate the total probability of testing positive, and we end up with 0.0594. Now, using Bayes' theorem, we can calculate probability of disease given test positive. Then we will end up with approximately 0.167. This means that even with a positive test results, there is only a 16.7% chance that the person actually has the disease. And this example shows the importance of considering both sensitivity and specificity when interpreting medical test results. Now, we're going to look at another example, which is involving email spam filtering. Say we are trying to classify an email as spam or not based on whether it contains the word free. Here are the details. So we have prior probability, which is probability of spam. So this is the initial probability that an email is spam, which is 20% or 0.2. And then word free in spam. So this is probability of having word free given that it is a spam. So this is the probability that a spam email contains the word free, which is 70% or 0.7. And word free in non-spam, which is probability of free given non-spam. So this is the probability that a non-spam email contains the word free, which is 5% or 0.05. And we want to calculate the posterior probability or the probability that an email is spam given that it contains the word free, which is probability of spam given the word free. And similar to previous calculation, we would need to calculate the total probability of an email containing the word free. So and it will turn out to be this. Probability of free equals to probability of free given spam times probability of spam plus probability of free given non-spam times probability of non-spam. So we have the data. Probability of spam is 0.2, probability of free given as spam is 0.7, probability of free given as non-spam is 0.05, probability of non-spam equals to 1 minus probability of spam, which is 0.8. And if we are to calculate the total probability of email containing the word free, it turns out to be 0.19. Now we can use Bayes' theorem to calculate posterior probability. So we are going to get the probability of spam given the email contains free, and it turns out to be 0.737. This means that if an email contains the word free, there is a 73.7 chance that it's spam. So we can see that Bayes' theorem can be used to improve spam filters by updating the probability of an email being spam based on its content. So application of Bayes' theorem. Bayes' theorem has a wide range of applications across various fields. Here are a few examples. Medical diagnosis. In this context, Bayes' theorem helps in updating the likelihood of diseases based on test results, improving diagnostic accuracy, and we talked about spam filtering and machine learning. So Bayes' theorem is fundamental in algorithms like naive Bayes filter, naive Bayes classifiers, which are used for classification tasks, and risk assessment. Bayes' theorem is used in finance and insurance to evaluate and update the probabilities of different risks and forensic science. So in this context, Bayes' theorem helps evaluate evidence in legal cases and thus providing a probabilistic framework for decision making. Conclusion. So in summary, Bayes' theorem provides a mathematical framework for updating probabilities based on new evidence. And Bayes' theorem is widely used in fields ranging from medicine to machine learning, and it helps us make more informed decisions. That's it for this lecture. Thank you everyone for listening.